plan is to first talk about the problem itself, and then I'm going to introduce some basic. I'm going to give a survey of the basic notions that we need to introduce to further our discussion, and then I'm going to introduce two methods, two potential solutions to the problem, and finally I'm going to compare them. So long before in developmental biology and also in genetics, there was this understanding that the relationship between the genotype and the phenotype was one-to-one. And also another understanding which was not really disclosed but still prevalent was that the genotype only seldomly affects the phenotype. This idea was first challenged by Waddington in 1942, and he proposed that maybe each gene can affect multiple traits, and also each trait may be influenced by a number of genes, and also maybe even things other than genes, such as the environment. And also he argued that maybe this interaction between the genotype and the phenotype is continuous rather than just being seldom interactions. So how do we model this Waddington's idea as a mathematical model? Well, we can imagine the cell as being part of a abstract phase space, and this cell can be influenced by a number of what we call driving forces, which are just nonlinear functions of the genotype and also the environment. And because this relationship between the genotype and the phenotype is continuous, the cell is continuously driven by these driving forces, which is, of course, just gives us a set of an ordinary differential equations, which is a dynamical system. A dynamical system is not necessarily a collection of ODEs. However, in this context, modeling the dynamical system as a set of ODEs makes sense, and we move on with it. And so Waddington also came up with a visual metaphor for this. He imagined a landscape and marbles rolling down the landscape, and each marble in this analogy corresponds to one cell, and marbles essentially roll down and accumulate in stable points of the landscape, whatever that may mean at the moment. And those stable points correspond to the differentiated versions of the cell. This metaphor was purely visual for Waddington. However, well after Waddington, people have realized that this analogy actually can become the basis of the mathematical framework that we use to study such systems. Before doing that, of course, we need to first introduce some notions. First of all, a steady point of a dynamical system, which I'm just going to refer to as a system from now on, is just any point where all the driving forces are zero. So if we also think of the system as a set of ODEs, the steady points are just solutions to the system that do not depend on time. So if we move on with Waddington's analogy, the two marbles here, or two states here, are both steady because they are, if we place a marble there, the marble stays there indefinitely. It can balance itself out there. Or in other words, the driving forces are zero in both of them. However, as you can see, the behavior of the two marbles are completely different. When I just make a small perturbation to the one on the right, it moves across the phase space quite a large distance. So we need to introduce another notion, and we want to say that, okay, the one on the left is stable, however, the one on the right is unstable. And this was first done rigorously by the Russian mathematician Lyapunov in 1892. And he defined stability as you see on the screen. I'm not going to read out the definition here, but this is just essentially a continuity requirement on the phase space. So stability is indeed a local property. Also, we call stable and steady states attractors. So if we go back to our figure here, the marble on the left, or the cell on the left is both stable and steady, so it's an attractor. Another way to read this definition is to say that a point is stable if any point that is near enough to it stays near it indefinitely. We can also think about it like that. And Lyapunov studied such systems in detail and come up with a lot of theorems and notions. The theorem that is important to us is his direct method, sometimes also called his second method. And this method allows us to test whether a point is stable or not. And we do that by coming up with another function called v. And all we want from this function is it to be, first of all, it needs to be positive definite with respect to the point that we are testing. And also the time derivative of it should be non-positive. And that's all, actually. If we find such a function, then this theorem states that, okay, then that point is a stable point. We call such functions Lyapunov functions. And to see this theorem in action, I've come up with a simple example. So let's consider this one-dimensional dynamical system, which is arguably the most simple one that we can consider. If we do not use Lyapunov's theorem, we can actually approach this analytically. This is a simple differential equation, and we know the solution to it. And if we examine the solutions or trajectories, we can conclude that the point at zero is stable, because whatever point we start on the y-axis or the initial condition, all the solutions just converge to x equals 0. So the point at 0 is stable. It is in fact asymptotically stable, but we are only talking about stability today. And so this is nice, but of course, for a given high-dimensional system, we don't know how to solve it analytically. So what happens when we try to solve the same thing using Lyapunov's theorem? Well, we just come up with a function. In this case, it's just a half of x squared. And also realize that the negative gradient of this function is just the system itself. So there is some motivation there. So this function is positive definite, and also the time derivative of it is just negative x squared, which is negative semi-definite. So by Lyapunov's theorem that we have mentioned, then the point at 0 is stable. So this is very nice, because even though we don't have a good way to come up with Lyapunov functions, once we find them, we don't need to come up with analytical solutions just to find out if a point is stable or not. So to really appreciate how hard the problems that we come across in biology, we need to understand the type of systems that we come across. First of all, many systems in biology are multi-stable, meaning that they possess a number of stable systems, not just one. And also they are non-gradient, meaning that they are not the gradient of another field. And also they are non-equilibrium, meaning that they are not in thermodynamical equilibrium. So we cannot really use results from thermodynamical theory to come up with results, which makes things a bit harder. And also they're high dimensional and nonlinear, which is, of course, always a bad thing. So yeah, so the actual problem is much harder. And if as we have also seen in the example, if the system is gradient, then the potential function exists. It's just the negative gradient of what the field that we are taking the gradient of. But most systems are non-gradient, of course. So the idea here is to come up with a quasi-potential that may or may not be useful to us. So we need to define what useful is, and that is done in this amazing 2012 paper. And that paper comes up with three requirements for a quasi-potential to satisfy. First of which is a quasi-potential needs to satisfy the stability condition of Lyapunov, because Lyapunov functions are essentially just local potential functions, and the quasi-potential also needs to be a potential function locally. So we need to preserve that sense of being a potential function. And also it needs to allow the computation of transition rates between attractors. Computing transition probabilities is the number one thing that biologists are interested in, and we want this quasi-potential to enable us to find the transition rates. And also it needs to permit a global ordering of the metastable states. What is a metastable state? It is simply just a stable state that is not the global minimum of the system. So these both of these states here are stable, but we call the orange one metastable. And we want the quasi-potential to permit a global ordering, meaning that we want to be able to say that, okay, this orange state is less stable than the red one. This sounds really trivial when you put it like that, but it is actually turns out to be a really big problem. Okay, so let's move on with the first approach, which is to deal with field decompositions. And when you work with field decompositions, the first theorem that comes to mind is the Helmholtz decomposition theorem, which is actually only a statement in 3D, but there are generalizations of it, which is called the Hodge decomposition theorem. But basically, it just means that this just states that any sufficiently smooth vector space can be decomposed into a curl-free and a divergence-free term. I am writing the divergence-free term as FC here, and the curl-free term can be expressed as the negative gradient of another scalar function. And if this f was if this f was a gradient system, then this fc would be 0, and u of h would already be our quasi-potential. However, most fields, as we have mentioned, are not. So the idea here is to, okay, maybe we can still make this decomposition, and maybe this u of h can give us a quasi-potential. But first of all, can we compute u of h this way? This turns out to be not a big problem, because we can just solve this Poisson equation, which can be done in with numerical methods, so it's not a problem. However, this u of h does not satisfy the stability condition, because when we take the time derivative, it is not non-positive, because the term that we end up with here is not going to be 0 or negative in general. So this fails. But the first lesson that we should take here is that, okay, the first thing that comes to mind when you're dealing with a problem turns out to not work, we shouldn't really be surprised, because it was the most obvious thing and it didn't work. So no surprises there. So maybe we think about this problem a bit more and come up with this new idea. So more stable states in the system are going to be more probable. So what if we impose a probability density function over the state space, which I'm going to call P? Well, first of all, the time evolution of P is known to be described by the Fokker-Planck equation. This is the sort of thing that physicists are well known for. They know how such things are described, so no problems there. We already know the behavior of such a probability density function. So the idea here is to, okay, maybe we can work with this Fokker-Planck equation to get a decomposition. And to do that, we need to also use a result from another theory, which is thermodynamical theory. And we know that a system at thermodynamical equilibrium, for a system at a thermodynamical equilibrium, the function P obeys the Boltzmann distribution. So if we just use this energy state here as our quasi-potential, then we need to have this proportionality between u of p and the negative natural log of p. And what if we use this and try to construct a constraint on the Fokker-Planck equation? Well, turns out when we do that, we come up with this equation 2, and this equation 2 constitutes a constraint for equation 3. However, when we check for stability again, this turns out to again not satisfy our stability condition, because this term is not going to be again negative or 0 in general. So this still fails. However, this is the second life lesson. Just because something didn't turn out to work doesn't really mean that we haven't made progress towards the solution, because we are actually done here. We just need to do the same decomposition, but this time we need to change our constraint to the following, that the gradient of the quasi-potential that we come up with and the remaining divergence-free part should be perpendicular, because when we do that by the exact same calculation, the time derivative of u norm is going to be non-positive, and we are done. So we have found a decomposition, which is the normal decomposition that satisfies the stability condition. And also we can solve for u-norm by solving the Hamilton-Jacobi equation. This is known as the Hamilton-Jacobi equation, and again, numerical methods exist, so we are not really concerned with that. Okay, so I'm going to introduce another approach, which is large deviation theory. Large deviation theory is the study of dynamical systems with a perturbation term, usually as just a small noise. And we do this by introducing a stochastic term to our normal dynamical system. And this is usually just small in magnitude. And we actually get a quasi-potential from large deviation theory. So there's this functional, which is called the Freidlin and Wentzell functional. And the job of this functional is just to assign a cost to each possible trajectory between 2 points. And we are skipping a lot of details here, but this is intuitive because this, as you might imagine, this just adds up the stochastic term parts along a trajectory. If we just leave the stochastic term part here zero alone here, it's just this term. So this functional is a good notion of a cost between 2 points. And using that functional, we can come up with this following expression, which I'm going to call V, and this can be shown to be a quasi-potential. This is a variational problem here because we are taking infirm over 2 variables here, as you can see. The unique infirm exists by variational principle, so that's fine. And this is good because V allows us to calculate the transition probabilities between 2 states, and it is given by this exact formula. So this is very nice. However, there is a problem here because V, as you can see, V is only given with respect to a single attractor in the system here. So therefore, it only provides a metastability ordering for a system of 2 attractors. Even if we just have 3 attractors, this just fails to be a sense of metastable ordering globally in the system. Also, solving variational problems is hard, which is not really a good reason. Also, it turns out we can generalize this to a global sense, but when we do that, we lose the transitivity property. And as it happens in math, when you lose transitivity, you also lose the sense of ordering. So there is this amazing paper which actually does this explicitly. And like when you generalize this metastability ordering of 2 attractors to general, you get some nonsense stuff like A being more stable than B, B being more stable than C, but somehow A also being more stable than C. Like it is nonsensical, and we don't want that. We still want an ordering. So although this works quite well, it only works for 2 attractors. So, and also the other amazing thing is that also the same paper from 2012 shows that there's a pretty simple mathematical relation between these 2 quasi-potential, the quasi-potential from a large deviation theory and the one from the normal decomposition that we have just mentioned. And they are related by just a factor of 2. And they come from very different mathematical backgrounds, but they are related by such a simple form relation. And I think this is one of the fascinating parts about this. And but we should still be careful because even though they are mathematically related, the quasi-potential from large deviation theory here is actually provides more information than u-norm here, because with just the u-norm we cannot really calculate the transition probabilities. However, V allows us to do that. So that's it. Like there's no good ending to this talk because the problem still remains open. There's not a good way to come up with a global potential landscape that is both respects, that is, 1, respects the stability condition, 2, provides an ordering, and all still allows us to calculate transition probabilities. It is an open problem, and as of yet, no one has found a good way or a practical way to do it, and that's why I wanted to talk about it. And here are my references, and if there are any questions, I'm happy to answer them. Thank you.